Hey guys, it's Dr. Calkins. This time we're going to look at chapter 10, or at least week 10, chapter 8. This is all about reactions. And we've spent several weeks covering on things that are in the organic and biochemistry kind of realm with nonmetals and other nonmetals, but now we're getting back to ionic compounds, how they can transform chemically into others, so balancing equations, that kind of thing. So remember, there's several types of ways to recognize a chemical change. This will take us back to chapter 1. You can look for a gas formation. Gas formations are typically for, say, hydrogen gas that explodes, oxygen gas that makes fires bigger, or even carbon dioxide that puts gas out. Those are the very common types of gas formation that you would see in a chemical change. You can also form a insoluble, what we call precipitate. We did this in experiment 1. We formed that bright yellow floating kind of suspension between potassium dichromate and lead nitrate. So insoluble, and this is going to be a topic later that I'll do in a separate video. It's about a half of your homework, recognizing precipitates from things that aren't insoluble, soluble in water ideas. Other things to look for are heat and light. So heat and light are going to be things that show up, say, with fireworks. Fireworks are going to have lots of heat when they burn the paper that has those coated chemicals, much like our other experiment at the beginning of the semester, to burn those pretty colors and produce light. And then lastly, what we're going to look for is that permanent color change. Color change that's not reversible, because chemical changes aren't reversible without other chemical changes. So as we look at reactions, there's a few things we need to worry about first. As we look at reactions, there's some molecules that hang out together, and we've covered these once before in the Lewis dot structure chapter. But remember, there are some things that are diatomic. Diatomic just means it has two atoms in their stable natural state. So things like oxygen, when you hear oxygen from now on, that's because they mean O2. Oxygen doesn't exist by itself. Nitrogen, same thing. Nitrogen gas is N2. You have those halogens like fluorine gas, chlorine gas, bromine, the liquid, and then iodine, the liquid. We never actually saw it as a liquid. It's a solid at room temperature and likes to sublime. The other ones that we have to worry about are hydrogen. When they say hydrogen, they really mean H2, because that's all that exists, because of their ability to become noble gas-like. So those are ideas that we haven't seen for probably 4 or 5 weeks in a row. So next thing we're going to do is, as we use these kinds of molecules and reactions, can we balance an equation? Balance an equation is just like balancing on a teeter-totter. We want to make sure both sides have the same amount of mass. This is based on the law of conservation of mass. So what that really means is, it means that both sides have to stay the same amount of atoms, same amount of weight, same amount of mass. So let's do an example that's relatively simple. We take hydrogen, which is H2. We take iodine, which is I2. But when they make a product, uniquely we get HI. You might think that that's weird, because if there's two H's here and two I's there, why isn't there H2I2? Well, the issue is hydrogen, being from group 1, it loves a +1 charge, like all those alkali metals. I likes a -1 charge, like all those halogens above it. And those charges cancel to make the hydrogen iodide molecule. So you could think of them as ions, or you could think of them connecting dots. It doesn't really matter for purposes of this chapter. But what does matter in this chapter is that we can recognize there's a mismatch in the number of atoms on both sides. So as we do this, we realize over here there are two H's and there's two I's. But over here there's only one H and one I. So that means that this side of the little teeter-totter is a whole lot heavier than the other. We want it to be equal. We want it to balance out. So the only thing that we need to do here is add a 2 in front of the HI. This is called a coefficient. Later in the semester it'll be called a mole. But if we add a 2 here, that multiplies across and gives us the 2 H's and the 2 I's that we need in order for it to have perfect balance, 2 H's and 2 I's on both sides. So to balance this equation, really what's missing is a 2 in this kind of position. We can keep 1s and that are kind of redundant, but imaginary in most cases for that. So let's try another example. Try another example. Let's try nitrogen with hydrogen. If we try nitrogen with hydrogen, we're going to see very quickly a different kind of matchup, because in this case, whether you think about it with nitrogen and its 5 valence electrons connecting to 3 hydrogens, or if we want to cheat like we did at the beginning of the semester and say nitrogen, like nitride's a -3, this is a +1, and we will cross those charges. Brings back painful memories, I'm sure. But notice the mismatch again. We have 2 H's and 2 N's on this side. And that represents the weight or the balance of that side. But right now we have 1 nitrogen and 3 hydrogens. So again, this side is still quite a bit heavier than this side. So if this were balanced, this would be, kind of way up here. We need them to be equal. If we need them to be equal, we have to realize that nitrogen and hydrogen are different, so we rewrite this into plus H2. Gives us our ammonia molecule. Hopefully, for sake of sanity, you'll realize that we have a difference of 2's and 3's. When that happens, we have to realize what does 2 and 3 have in common? The lowest common multiple is a 6, so if we make 6 on both sides, in this case, 2 times the 3, keep in mind it's also 2 times the 1, it's imaginary, would be the same as 3 times the 2. That would give us 6 hydrogens on this side, and that would equal the 6 hydrogens on this side. Magically, though, that 2 times the 1 gives us 2 nitrogens, and notice we already have 2 nitrogens, and those together have perfect balance. So it's almost like you're keeping score. You realize you have nitrogens and hydrogens. You have the reactants in the beginning and the products in the end. And eventually you'll notice that you started out with 2 nitrogens and 2 hydrogens. Because of the ammonia molecule and that charge crossing idea from earlier, we have 1 nitrogen and 3 hydrogens. Recognizing this first is important because there's the mismatch. Recognizing that this is just double, but this is something that's not double, is the quickest way to realize that if we times this by 3 and times this by 2, they're going to be equal. And we got lucky in that case because that 2 also applies to that whole molecule, so this was also times 2. This 2 is this 2. This 3 that we needed is this 3. And nitrogen didn't need anything, it's just a 1. So let's do one more example, and then we'll have plenty of practice in the lab book coming up, as well as the homework. This one's going to be a little bit more intimidating to look at from the get-go, but it's going to follow the same kinds of issues. This one's going to have much more going on, so we're going to take aluminum and sulfate. Painful there. Aluminum in group 13, a +3, sulfate a -2, that's a T4 ion that we saw a while back. Cross the 2, cross the 3, we get aluminum twice, sulfate 3 times. Barium and nitrate. Barium a group 2 alkaline earth metal, that's a +2. Nitrate, T4 ion with a -1. Cross those charges that are different. We get barium nitrate. And then uniquely in this reaction, much like our reaction that we did at the beginning of the semester, where we mix those 2 together and got yellow, we're going to give aluminum, the other partner, nitrate. in this case aluminum, +3 still, nitrate, a -1 still, cross the charges and we get a 3 out here instead of a 2. Different families, different charges. And then what's left over is barium with a +2 and sulfate with a -2, and that's a perfect match. They can just squish together and get barium sulfate. So the reason that I show you this example that's a little bit more intimidating to look at is if the atoms are together in a certain group and they stay in that certain group, don't make it tougher on yourself. I always like to start with the biggest and the scariest. In this case, they might all look scary, but this one at the beginning, we have 2s and 3s. So why not let's start there. If there's 3 of these sulfates, let's just make sure that over here, since this barium sulfate comes as one unit, we get 3 of those. That'll give us 3 of our sulfates that we need because imaginarily there's only 1 per unit. But unfortunately that does apply to barium as well. So we're going to need 3 bariums to make up for it over here. That'll give us a 3 to 3 match that we need. Unfortunately at the same time, that's a 3 times a 2. So just like we had 3 here, we're going to now have 6 here. To get 6 to match on the other side for nitrate, it's already at a 3, a 2, and a 3 will make 6. Unfortunately, a 2 and a 1 also gives you the 2, but guess what aluminum had waiting in the wings? The 2 that we needed. So don't make it tougher. Don't look at all the oxygens and blow your mind and worry about how they changed. If sulfate stayed sulfate, leave it alone. If nitrate stayed nitrate, leave it alone. Use it as a unit when you balance, not as individual atoms, and it's going to be a whole lot easier. So this is a kind of introduction to balancing equations. There's a lot of practice in the notes, the lab book, and some of the experiments coming up.